Okay, so this is just another Spartan tutorial video to show you how to use Spartan to calculate IR and NMR spectroscopy. And then I'll also use this to show you how to do calculations on carbocations, free radicals, and carbanions. So I've already built this molecule. So this is an anhydride, so I just built this molecule to illustrate a feature in IR where you can look at symmetric and asymmetric stretches, for example. So so we have the molecule built. So what we want to do now is going to go to Setup, Calculations. So I would recommend the first thing you do is calculation at this level of theory, MMF. And if you do that, then you can see here that you can choose to compute the IR spectra. So I've already done that at this level of theory, and then I already did the calculation. So after you do that, then optimize the geometry at this level of theory, so density functional theory, and pick this basis set, B3LYP, and then 631 G star. And then we're just going to click submit. And it says it's down here, it's going to take about 1.1 minute, but I've already optimized the geometry, so hopefully it goes a little bit faster than that. And then we can click this as well to turn on, so we'll compute both the IR and the NMR. And then click submit. So you can see it, since I'd already optimized the geometry, it's already done. So what we do now is we can click this icon here. So that's for spectra. And then if we go over here to the plus and click IR, then it'll show you the IR spectrum here. So if we click this, then it where's it at? That one. So this one will show you the table for the calculated, and if the experimental IR is available, then it'll pull that in as well. Or once you click this, then it'll pull the experimental from a database somewhere if it's available. Okay, so this just tells you all of the different wave numbers where the peaks are at. So for this molecule, it's a pretty simple molecule, but I chose this molecule so that we could look at the CO double bond. So the CO stretch should be somewhere between 1700 and 1800. And with the anhydride, you can have what's called a symmetric stretch, where these are both stretching in the same direction at the same time, or you can have an asymmetric stretch where one of these is stretching while the other one is compressing, and you'll be able to see that. So if we go down here and if we drag this around, and if we drag this onto that peak, then you can see that that is the symmetric stretch. So both of these C double bond O's are stretching in the same direction at the same time. And then if we drag it over to the smaller peak, then you can see that that is the asymmetric stretch, where this one is stretching while that one is compressing, and vice versa. So you can see over here in the table also, you can click these on and off. So that's the asymmetric stretch. And this calculation calculated that to be at 1862 inverse centimeters. And then the other modes, so the CH bonds bending and so forth. So these are just the different vibrational modes for the molecule. Come on, there we go. Okay, so we can also go here then and we could click on experimental, and if the experimental spectrum is available, it'll pull that in. So we can see here that the red is the calculated IR and the blue is the actual IR. So the actual IR of this has the C double bond O symmetric stretch at 1832, and the calculated was at 1862. So the calculation did a pretty good job, and the asymmetric stretch, I assume, was this here at 1779, whereas calculated it's at 1788. Okay, so we can go back here if we want. We can turn these back off and not display them. If we want to display the proton NMR, It's pretty boring proton NMR. It's only got the CH3 and their equivalent, and there's no neighbors, so it would just be a singlet. They're at 1.7879 ppm. And if we go here and look at the carbon-13 NMR, then there's your carbon-13 NMR. Of course, there should be two carbons, the CH3, which are equivalent, which is this. So where's the C double bond O? Well, it's off screen right now, so let me turn, let's get, so if I put, since I'm on a Mac book with a trackpad, if I just put both fingers on here, and if I just drag to the left, then it'll bring the rest of the spectra on. So it's contracting the spectra. If I go to the right, then it's expanding the spectra. So there's the C double bond O. And you can see when I click on this, it changes these two colors. So that's the two carbons. C double bond O carbons are at 166.5. And if I click that, then these two carbons turn yellow, so those two carbons are at 20.5 ppm. So that's basically how you calculate IR and NMR spectra. So the carbon-13, let's see if it's available experimentally. Yeah, so there's your experimental. And so it did a pretty good job of reproducing experimental. So you can see it barely missed in terms of the chemical shift. So 21.8 experimental versus 20.5 theoretical. And for the C double bond O, if we want to get this on the screen, okay, let's see, how can we get that to stay on the screen? Well, if I played around with this long enough, I guess eventually we would figure it out. There we go. Okay, so there's our C double bond O. So 166.5. Whoa. What has happened here? I don't know what I did, but you get the point. Okay, so what else should we show you how to do? Let's take a little bit more interesting molecule. So let's just close that, and let's go to a new build. Let's just pick something that's got some splitting pattern in it. Okay, so let's go here to minimize to clean up that structure a little bit. And then let's set up calculations. So for equilibrium geometry, let's first do MMF. And let's go ahead and calculate the IR. And submit. Okay, so it's already done. If we just look at its IR right quick, there should be a C double bond O. It would be the main feature of this molecule. And that C double bond O is here. So there you go. There's a C double bond O stretch at 1824. So this is not doing a very good job of predicting where that should really be at. So if we go to a higher level of theory and do this calculation, so let's go set up calculations again. Whoops. Let's go back to density functional theory, that low basis set, and 1.6 minutes. Let's hope it doesn't take that long. Maybe let's try something different. There we go, 10 seconds. So this is still quantum mechanics, so it should do a better job of calculating where that should be at. And we can do NMR as well. And now we wait, so the job is submitted, and hopefully it finishes quick. And now it's done. Okay, so let's have a look. So the IR, 1957, that's not even close to where it should be. So this is not doing a very good job of calculating where it should be as well. Let's see what the see if the experimental is available. Yeah, so you can see that it should be way down here around 1720 probably. So we'll try the maybe density functional theory and see if it does a better job. But let's look at the proton NMR. Okay, so now we can blow it up a little bit. We can see our splitting pattern. So in the molecule, so in the molecule, what should be the furthest downfield should be the CH3, and it should be a singlet. So this will be your CH3. So you can, well, that should be, it's those 3 hydrogens on that carbon, right? And then if we zoom in here, you can see that here we have a triplet and another triplet, and this triplet should be the one next to the C double bond O. So it's those 2 hydrogens. And then this should be 6 peaks. So that's for that CH2, and then this one is the furthest away from any of the hydrogens, and that has 2 neighbors, right? So this CH3 has 2 hydrogen neighbors here. So N plus 1, 2 plus 1 should be a triplet. And you can see, and they're the furthest from oxygen, so they're going to be the furthest upfield. So you can see that that triplet is there at about 0.93 ppm. Okay, so that's how you do spectroscopy using Spartan. And there's some other features you could use this for, but that's good enough for now. Okay, so let's show you how to do some calculations with free radicals and carbocations. So if we go to a new build, okay, so let's say I want this carbon in the middle to be a carbocation. So I'm going to go here to my eraser, and I'm going to erase that. So now that carbon only has 3 things attached to it, so 6 electrons around it. So if I go to set up calculations, so let's go to a low level of theory to start with. Not that low, I guess. No, what am I doing? Yeah, this is good. Okay, equilibrium geometry, MMF, nope. We at least need to go to semi-empirical level so that we have this feature available. So it's a carbocation, so the charge should be +1. And all of the electrons are paired. So it's not, if we wanted this to be a free radical, we would change that to 1 unpaired electron. But here all of the electrons are paired. So this is a carbocation. Before I do this, if you notice the geometry here, let's cancel this right quick. So right now, it was a tetrahedral carbon before I took that position off. And now it's only got 6 electrons around it, carbocation, which should be the hybridization of a carbocation. It should be sp2 hybridized. So let's make that a carbocation, submit. And it's already done. And if you can see that it flattened it out because that's sp2 hybridized, it's trigonoplanar. Okay, so if we wanted to look at the charge on this carbon, so let's go here to display output. And we can go over here to atomic charges. Okay, let me drag this where we can see it. Let's turn on atom labels, so model, and turn labels on. So we can see that this carbon in the middle is carbon 1. So now if we go back over here and look at our atomic charges, carbon 1 has a +1 charge on it. 2, 3, and 4 are all negative charged. And so, of course, the carbon in the middle should be the one that's positive because that's the one that's electron deficient. So that's how you can do some calculations with the carbocations. And if we wanted to know the energy, so if we display output, there's your energy. So if you remember, the more negative or the less positive the energy is, the more stable it is. So if you compare different carbocations, primary, secondary, and tertiary, the one that's tertiary should have the least positive or the more negative energy. So if we go to a higher level of theory here, setup calculations, so if we go to Hartree-Fock, so ab initio theory, now it's done. Oops, failed. That's not good. What happened? Setup calculations. Why did this fail? Well, I'm not sure why it's failing now. I did not have this problem earlier. Let's go lower level of theory. I'm not sure what's going on. Let's try a new build. So we'll just keep it real simple. So let's take position off of this. So now that's going to be our carbocation. It's going to be a primary carbocation. So +1 charge, submit. Okay, it's done. Now let's try to go into ab initio theory. See what happens. Wow, I did not have this problem yesterday when I was doing this, so I'm not sure what's going on. Okay, well, I'm not sure what's going on here, so if you have this problem, let me know. But I did not have this problem yesterday. So let's try a free radical. So if we take that, and let's take off one position from here, and set up calculations. So let's go to PM3, and now it's a neutral. Free radicals are neutral, but they do have one unpaired electron. And submit. Okay, so now if we look at the output here. Okay, so again, we want to look at the energy, and the more negative that is, the more stable it is. Not that one. Yeah, I think this one. And then let's look here at the atomic charges. So now that it's a free radical, there's a new column here called spin density. And let's turn our labels on, see which carbon is which. So this is C2 is where the free radical is at. And so if you can see C2 here has positive spin density, so that's where the free radical is at. Okay, well, all of these calculations are not working for some reason. So, and I don't see that I'm doing anything different than yesterday. So I'm not sure what the problem is. So we'll see if they work for you or not. And I'll try to explore and see what's going on. Why did this work yesterday, but it's not working today? Well, now it worked. So so what I did is I clicked this off and now it's working. So now if we look at the output, so now you can see the energy is now given in Hartrees instead of kilojoules per mole or kilocalories per mole, but there's a conversion factor where you can convert from Hartrees to kilojoules per mole or kilocalories per mole. Okay, so that's basically what you need to do for these problem sets in order to do spectroscopy and the calculations on carbocations and free radicals.